a quick reminder of what we did from last time. So at the end, we talked about a very important example of a quantum Wreath product algebra. This is due to Hu Jun. So he first constructed this algebra as a subalgebra of a larger Hecke algebra of type A. In particular, this is generated by a parabolic subalgebra of this subgroup together with a very peculiar extra generator Hn. And we talked about an explicit formula for this Hn last time. Oops. So this sits inside a larger Hecke algebra of type A. And then we talk about a presentation of this guy. So we think this should really be treated as the Hecke algebra for this Wreath product Sm Wreath S2, which is not in general a Coxeter group. So this is how it is done. You consider a base algebra, which is a smaller type A Hecke algebra, take its tensor. And you have one extra generator corresponds to this one. And the relation for this new algebra satisfy two relations. The first one is this extra generator squares to some element in the center of the tensor product. And then you talk about how this extra generator interacts with element in the tensor product. So you have H almost commute with, say, element here, but you flip the two tensor factors. So these B and A's are in the Hecke algebra. And then you can find an isomorphism by sending elements in the parabolic subalgebra to this tensor product and this extra generator to this one. So I think the important viewpoint here is we should really consider this as the quadratic relation as in the usual Hecke algebra. So typically we were thinking of something like T1 squared equals to Q minus 1 T1 plus Q. But those coefficients are in the ground view. But we really think we should accommodate this algebra by treating the coefficient in the tensor product instead. So let's talk about a axiomatized way for these Wreath product versus quantum Wreath product again. So for the Wreath products for groups, you define this Wreath product using a semi-direct product by the symmetric group.
So is this element Cm easy to write down explicitly?
Yes, so this is the square of that one. So we have a explicit formula for the, yes, but this takes a long time to write it down. So yeah, right. So only with an explicit formula, this relation makes sense. Right. Okay, so here, when you deal with a semi-direct product, you need to identify, say, elements in different order, I should say. So if you locally, you can consider element GH in capital G squared. And you also have element in the symmetric group part. So if you look at, say, this simple transposition, when you pass this S to another side, you flip the order of the order. So this is the local relation for the Wreath product, and you can define similarly the global relation for the D tuple of this direct product. And since we are talking about just the symmetric group, you have also local relation that this simple transposition squares to 1, and you have braid relation of this form. So our quantum Wreath product is a procedure of finding a deformation of such procedure for groups. So instead for groups, we look at, in general, associated algebra. So we have a new algebra that is generated by the default tensor of this associated algebra together with heck-like generators. But these are formal symbol at the moment. And then for this Wreath relation, you really need to deal with local relation like this. You have H and the element in the tensor product AB lies in B tensor 2. Then when you pass H to another side, you create a new coefficient. So this sigma is, in general, any endomorphism on B tensor 2. And then you have to have an arrow turn. So in the previous example, we have sigma being just the flip map, sending A tensor B to B tensor A, and rho is the zero map. But we then realize that if we allow this arrow turn, we can also take the affine Hecke algebras and O its variance into consideration. And then for the quadratic relations, you have H squared equals to SH plus R for some SR being element actually in the center of B tensor B. Maybe I should also write that here, rho sigma R endomorphism on B tensor B. And finally, you have the same braid relation. So philosophically, this is how why we call this a quantum Wreath product, because this algebra is subject to all the relations, which can be regarded as a quantization of relation in a Wreath product. Any questions so far? Okay, so now let me be more precise. How you write down an actual definition from this local relations. So this is.
So there's no Q problem in the definition.
Oh, sorry. Q here is a quadrupole. You can have the freedom to choose those elements, right? So once this is determined, you have a local Wreath relation and a local quadratic relation, and you can now define. Yes, so maybe I should say, sometimes I omit this Q. Right, so.
S and R on the line should be indexed by H. H has an index, so S and R should be indexed by I.
Oh, I'll explain that. So here, these are only local relations. So in the actual definition, you have to embed this into the I and I plus 1 position. So this is how this is done. So this is very recently formulated due to myself and two of my collaborators. And now, to be precise, I just tell you that this is, in general, a associative algebra over any commutative ring. And then Q is what I wrote. And the first twos are in the center of B tensor B. And this latter two are endomorphism. And then for any element, you can say X is either S or R. You can define, say, the corresponding element sitting inside B tensor D. So this is just putting 1 on the first I plus 1 factors, and you tensor an H, and then 1 for the rest. So this is an element in B tensor D. And you can define similarly for any such endomorphism. You have this map sending any.
The last one without minus I. The last one I without minus 1. The int is
Oh, no, because there are 2 factors here. So, right. So this is in B tensor B. Okay, so now you just apply those phi on the I and I plus 1 factors, and then the rest are the same. And then, so I can precisely give you the relations. And so we have braid relation for the type A braid relation for H, and then I have HI squared equals to SI HI plus RI, and for any element in the default tensor, you do this. Okay, so this is there's a one crucial difference between this and some like algebra you've seen before. So in those algebras, when you look at the quadratic relations, you can almost talk about a subalgebra generated by such Heck-like generators. But this is not the case here. In general, if you take this, I think you will likely get the entire thing. You take the algebra generated by this. So I think the right idea is to consider this not as a subalgebra isomorphic to a finite Heck algebra. The right viewpoint is to treat these as something that has a quotient which is isomorphic to a finite type Heck algebra. So by this, I mean you need to consider when B is an augmented algebra. Actually, let me talk about that later. Okay, so yeah, I just realized I need to talk about the basis first. So here you have a very vague definition, but when you're defining an algebra, if you randomly write down some relations like that, it is possible that your choice of parameters is not good enough, so you impose unnecessary relations and end up your algebra is trivial, which is 0. So the first question is, when does these algebra have an appropriate size? So I mean, when it has a basis of this form. Say, if you pick first a basis of your base algebra, and then since the braid relation holds here, you can define HW using any reduced expression. Then what we're looking for is a basis of this form. So I can write something like B lambda. This is B lambda 1 tensor B lambda D. Not a good idea for now. So let me put it here. HW, each lambda I is in the index and W is in the symmetric group. So this forms a basis. if and only if something holds. So this star is going to be a set of conditions on the choice of parameters. So the problem is not is now finding the parameters such that this has a basis. You can imagine it is easy to find some necessary conditions, assuming this is.
Can I ask a question? So when even for even for this to be an associative algebra,
Oh yes.
the conditions of this cube,
Right, right, right. That's totally correct. So it is, I think, highly non-trivial to describe what are the conditions to make it first a unital associative algebra and then it has a suitable basis. Okay, so right. So the first theorem for today is about finding the suitable conditions, which will be proved at the end, and then I will talk about some other problems in mind. So, as I said, the purpose is to study the older structures on, say, the base algebra B, under what conditions can be upgraded to those properties for the quantum Wreath product algebra. And one of the essential property we have in mind is the Schur-Weil duality. So we are now in a position of determining some of these conditions, making it possible to upgrade the Schur-Weil duality from, say, the base level to on the level of the quantum Wreath product algebra. So let me be very vague. So we now need B to be a symmetric Frobenius algebra, which means it has a trace map that induces a Frobenius bilinear form. And then you need certain condition on a splitting of the tensor space corresponding to this B action, which this is not part of the theorem. So I will talk about those relations between these conditions, but this usually implies Schur duality for B acting on this tensor space. And we will show that once you have the splitting plus some extra conditions, you can get a splitting of a new tensor space coming from taking the default tensor of the lower tensor space, which has an A action. Oh, by the way, A is this quantum Wreath product. And then this implies a Schur duality for the new algebra. So in the literatures, you can find, say, Schur duality for all the variants of the Hicke algebra, but they are all given by a, I would say, case-by-case analysis and using different approaches. So for this, we hope that we can remove this requirement that it has to be a finite dimensional algebra and give a uniform approach to all these Schur type duality. So this is not what you should do in an industry. You do pick an arbitrary algebra, prove a Schur duality for it. There should be a streamlined procedure. You should be able to check some condition, and then voila, Schur duality holds. Okay, so like I said, let me make a remark on the quotient part. So this, for this, you need a definition of an augmented algebra following Ginsberg and Kumar. So this is an algebra over K with co-unit. And for any augmented algebra, you can define an augmentation ideal, B plus. Yeah, let me write it down. Which is, by definition, the kernel of this co-unit. And this is a two-sided ideal of your algebra. And then you can define further the notion of normal subalgebra. So this is a normal subalgebra of some larger algebra if A times the augmentation ideal equals to A times this ideal on the other direction, and hence you can get exact functors by tensoring over B on both sides. And so, by some homologic algebra, you get a notion of a quotient algebra. So I write double line to denote that you are really taking the quotient of this AB plus or BA plus, and this is really isomorphic to A tensor over B with K or the other direction. And then one can show it that if something holds and B is augmented, and also assume that B is augmented, then your quantum Wreath product, yeah, let me write it this way. Quantum Wreath product algebra, quotient B is isomorphic to the Heck algebra of type A, which is generated by those Ti modulo the braid relations for Ti, and the quadratic relation is the usual one. You take the co-unit on S and R. So this is really a finite type Heck algebra. So this is used in studying the representation theory for the Hu algebra, but I don't think I will cover that for today. But I mean, this is some, I think, different viewpoint. You should not consider the element Hi and think they generate a Heck algebra inside. You should think they are responsible for making a quotient when it applies. Okay, so let's then talk about the necessary conditions in theorem A. So the idea, let me use a fancy language, that such a basis exists. That means there's no ambiguities for the following expressions. So the first family is some two-strand relations. So you have something like this, two crosses followed by an element in B, tensor B. And then you have one cross and then two elements in B tensor B. So this is to say that whenever you see such a diagrammatic expression, there shouldn't be any ambiguities. You can say, oh, sorry, I'm missing one more cross over here. Because whenever you see such a diagram, you can either resolve, say, this part of a diagram first, or then resolve, or you can do resolving this part of the diagram first. This is equivalent, say, using algebra. This is h times h squared equals to h squared times h. So only that you get an associated algebra structure. So then you want to compute whether h squared first times a is equals to h times h a. You resolve this first using the Wreath relation and then do it again. And for the third condition, third expression, you want to check whether HAB is equals to HAB. And actually, this is one, I think, important expression that we need to look at. So, for HAB, because we want it to be a associated algebra, these must be the same. For the left-hand side, what you do is, maybe I should use a different color again, just for clarity. You want to resolve this HA using the Wreath relation. So in the parentheses, you get sigma A H plus rho A, and then multiply by B. And now you get HB again. You can apply the same Wreath relation, but for B. Plus rho AB. And then on the right-hand side, you apply this to this element AB in the B-fold tensor. So you get sigma AB times H plus rho AB. So in order to have the two sides match, you must choose your sigma and rho such that this equals to that, and the term without H equals to the other constant terms. So you get the requirement that sigma has to be a group homomorphism, and then rho has to be a sigma derivation. So this is equivalent to saying that rho is a sigma twisted derivation. This is almost like the Leibniz rule, but you have a twisting by sigma at the beginning. And let me call this set of equation star 1. Okay, so we can imagine, we can write down the conditions for all these guys. Some of them are meaningful, like this one, but there are some other ones which are really nasty. So let me give you an example where I cannot really explain what's that for. Okay, so this one is actually okay, has no ambiguities, if and only if you have the interaction between sigma and rho, sigma and rhos and SR are rather nice. So the difference between these measure the sigma map. And then you have H2A has no ambiguities if and only if something nasty. So this is the right multiplication with respect to the choice of parameter R. This is equals to the right multiplication S then sigma square plus rho sigma plus sigma rho, and there's another one. Oh, sorry. Here, this is RS sigma. And for this one, it is rather artificial, but we will see. We'll prove it at the end. This is actually needed for the sufficient condition of the basic theorem. And by the way, let me call these guys star 2 and star 3 for now. And you guys don't need to memorize what those are. You just need to know that, corresponding to each of this strength, we have some set of conditions. Okay, and so here are only the two strength conditions on B tensor B. You can imagine there are some 3 or 4 strength conditions in general, but we will only use some of them.
Oh, you don't have the first one, AB top and the cross down. Oh, you don't have that.
AB cross.
AB top.
Oh, okay, so this holds if and only if this holds. Yeah. So you can reduce some of the expressions by symmetry. Right, so they are also 3 strength relations. In general, you can pick a, say, in the 3-fold tensor and consider something like this. And then, let me draw this. And I don't really want to write down, but there are a bunch of sets of equations here. Let me just call this star 4 and star 5. And, okay, I should really make a remark here. So I'm claiming, so they are more than this. They are actually something else. Say, if you want to prove it from the graphical calculus point of view, you can also write down some 3-fold, sorry, 3-strand relations like this. But we will show that this is not needed. This will be a consequence, assuming star 1 to 5. And I mean, there's a reason for that, but we don't know how to do that at the moment. But I just give you an idea that we don't just list every possible relations. We claim that, actually, we prove that star 1 through 5 are the necessary and sufficient condition for this algebra to have a basis. Okay, so if this is a little bit painful to watch, you can simplify some of these conditions by assuming, say, rho to be the 0 map. And maybe you want to assume, which is always happening, sigma is the map sending A tensor B to B tensor A. Then these relation simplifies to the following. R equals to sigma R. This difference, right multiplied by R is 0. And then the right multiplication of S times identity minus sigma is 0. So for some of the cases when the Wreath relation is just swapping the terms, those are actually not bad to check. The non-trivial case happens when rho is non-zero, which corresponds to the affine Hecke algebra family, but that can still be done. Okay, questions so far? Yep. Okay, so with this in mind, let's talk about how you realize these algebras in the literature as a constant Wreath product algebra. So let's look at the Who algebra again. We want to set B to be the Heck algebra of type A. So I think this is a very important example of algebra. And like I said, we have firstly the local relations A squared equals to ZM, and then H A tensor B equals to B tensor AH. So in this language, you really need to choose your S to be 0. R is this special element in the center of B tensor B, and then sigma is the flip map, while rho is 0 map because there's no extra terms from the right hand side, and then you just need to check that they all satisfy. So for example, when S is 0, this entire thing is 0, this is also 0. So and there's just one thing to verify, which is this special element is invariant under the flip map, which is not straightforward, but it is still checkable. But since we didn't talk about the explicit formula, so I'll skip it for here. But I'll just tell you this: there is a non-trivial calculation here.
So you check if you have any element invariant under
the flip map.
And it's always an algebra.
I think you can define, say, A squared equals to that, and you choose the same Wreath relation. You can define an algebra, and maybe they are isomorphic. I think they are isomorphic. As yeah.
If you choose 0, it's not.
Oh.
0 is not set.
Right. So I take that back, and then okay. So they are not isomorphic. Yeah, I suspect some of it's non-zero.
I'm not sure whether.
Yeah.
0 is also invariant, I guess.
Right. It is invariant. Right. So what I really hoping is this describe the Heck algebra for the Wreath product Sn with S2, as long as this square to something that is non-zero and also invariant under the flip map.
So I'm just wondering whether maybe this is not so hard, but like the Heck algebra of type B.
Right.
How is this related to this?
Okay, so this is a quotient of the affine Heck algebra. So you have to go through. Yeah, you have to go to affine.
Okay.
Right. Mm-hmm. That's a very good question, which I will talk about like in 3 slides. Okay, so the next one is the affine Heck algebra. So here you want to set the base algebra to be a commutative algebra, which is the ring of Laurent polynomial over a single generator X. And then I claim the local relation you need here is A squared equals to Q minus 1 times 1 tensor 1. This is the H plus Q times 1 tensor 1. So I'm using one convention, but you can, of course, change this Q minus 1 and Q to V inverse minus V and 1 if you like. And then for the Wreath relation, we want to prove that it suffices to consider the Wreath relation for X tensor 1. The rest will be uniquely determined from this Wreath relation. So this swap the 2 terms. And then for the arrow term, this is minus Q minus 1 times 1 tensor X. So this described as N R. Sigma is, again, the flip map. And rho, at the moment, it is only defined on X tensor 1, and it sends X tensor 1 to the extra term, which is minus Q minus 1 tensor X. Okay, so what I claim is, assuming only that rho is a sigma twisted derivation, then this uniquely determines that it sends an arbitrary element to the de Morgan operator times rho x tensor 1. Okay, so let me give you an sketch of the proof. Oh, by the way, so
here you don't need to specify x minus 1 condition. Negative.
the negative will also be determined by this one. Right, so if you, oh, by the way, I haven't defined what a de Morgan operator is. So this is itself minus the reverse over x tensor 1 minus 1 tensor x. So in general, it'll be a sum of x to some power, tensor x to some other power. It depends on whether A has a larger x power or B has a larger x power. And then, so this is basically a quick induction. Let me just give you a flavor. So let's abbreviate this by, say, beta. And then for any such element, you want to apply the twisted derivation condition. You split this x to the I tensor 1 into two parts. Which means you get sigma x to the I times rho x tensor 1, which is beta, plus rho x to the I minus 1 tensor 1 times x tensor 1. So you get 1 tensor x to the I beta plus something you can get by induction. So by finite times of iteration, you get beta times 1 tensor x to the I plus 1 plus x times x to the I plus 2 all the way to some final term, which simplifies to this de Morgan operator. Oh, by the way, here, let me assume first I is greater than or equals to 1. If I is negative, you can prove the same way. So this describes, on one hand, how you get this formula, and then you need to prove the other one, and those are all similar. Oh, by the way, at some point, you need to consider evaluating this both ways. And by matching the two, that tells you rho 1 tensor x will be negative beta. And so you can then deduce a general formula for an arbitrary element of this form. So this is uniquely determined by the value on x tensor 1. Okay, so I hope this part is easy. And then this makes the verification of star much easier. So imagine you have O-bound verification that has to be done for any rho or sigma map. But without this formula, that is, I think, hopeless. But from here, you can see that there is only, it is now reduces to a finite number of verification. And then one can show that under this choice of parameters, this Wreath product really realizes the affine Hecke algebra, which is given by this. So our Lorentz polynomial Wreath HD is isomorphic to the extended affine Hecke algebra, which is by definition generated by elements in the root lattice and also some Hecke-like generators. So here, lambda is a d-tuple then you want to modulo the braid relations for those TIs. And then the quadratic relation is like this. And then you describe this lambda part as a group algebra of the root lattice. And then there is a famous Bernstein-Lustig presentation relation. So alpha corresponds to the simple root, or in this convention, 1 at the ith position, -1 at the I plus 1th position. And so what I claim is, and this is probably not new, but this local relation describes precisely the Bernstein-Lustig relation. And the isomorphism sends x to, maybe I should go the other way, y lambda to x to the lambda 1 tensor x to the lambda d, and this ti is mapped to hi. Okay, so this is answering Shun's question. How about type B Hecke algebra, or in general Ariki-Koike? So at first, we were hoping that these can be realized as another quantum Wreath product, but we just realized this is fundamentally wrong. You cannot do it. You have to go through the affine. So I mentioned this last time. This is the quantization of the generalized symmetric group, which is the Wreath product of the cyclic group by the symmetric group. So you have a special generator Y and those type A generator TIs. And in the literatures, it is usually considered that you want to mod out the braid relation for a type B thinking diagram. But from our viewpoint, I think this is a misleading information. So this part should be we should pin this down and give it this a different meaning. So by this double edge, this means y t1 equals to t1 y t1 y. Let me deal with the easier parts first. Sorry, I changed my mind. I'll talk about this one first. Let me write it here. So what I'm thinking is this should be regarded as putting y at the first composition tensor factor. Sorry, T1 y T1 is a transfer from the first factor to the second factor. So this type B braid relation is just to tell you that y tensor y is well defined. This gives you the B tensor D structure on the nose. And then you have some other relations. For example, TIs, those type A generators, satisfy the usual quadratic relation, and there's a extra cyclotomic relation for this y. So these QIs are parameters, which is described here. This is 0. And when you set m equals to 2, you recover the Hecke algebra of type B. And I'm saying this, so I think one idea is when people can do some theorem for type A, they will try to generalize to type B, type C, go through the list of this thinking diagrams or simple Lie algebras. But I think this is not the reason that it can be done. This is not because it is a simple Lie algebra or coming from the list of thinking diagram. This is all because they are essentially of type A. You just take something of type A, take a Wreath product, which is still a type A process. So this is telling you that things you can do is essentially of type A. And there are some similar observation for affine Hecke algebra of type B and C. You can try to do this by taking the Laurent polynomial from one generator to some Laurent polynomial of 2 generators, and you take a similar quotient to get the affine Hecke algebra of type BC. Some like Schur duality for those algebras can be done because this is essentially of the form as a quantum Wreath product. And that's also a reason you really can proceed, say, the approach to those exceptional types because they are fundamentally different.
While the quantization for cyclical CM is so complicated, the last line.
Right.
Why?
Why?
Why not just one parameter?
So I think this is just because when you are recovering back, you are, so at a specialization map, you set Q equals to 1, but you want to specialize Qi to the root unity to some power. So they really has to be different parameters.
But for the case, it's still one parameter quantization. Because C is a quantization parameter. But now you do have only n quantum numbers. Right,
okay, so another reason, when you consider the case m equals to 2, this is Q, Q1, Q2. This is a Hecke algebra of type B. So then the Q1 and Q2, as you said, is really one parameter. So you can do some algebra and make it firstly, one parameter for the type A node and one parameter for this special node. But then sometimes it really helps to specify these Q to different numbers. And we will see that it is helpful to set capital Q to 1 while Q is generally some non-1 number. This is very useful in the type D situation and in our Hu algebra situation. So I'm saying these QIs, as you said, can essentially be one parameter, but these special parameters has to be different from the type A parameter. If that helps.
Because in phase, cycle do always the one parameter.
Right. Sorry, I'm saying this can be made into one parameter. I agree. Okay. Oh, yes. So I haven't finished. So the fact is, this Ariki-Koike algebra is going to be a quotient of the quantum Wreath product modulo the ideal generated by putting the cyclotomic relation on the first tensor factor. And then this y is sent to putting x on the first tensor factor. And as I said, this Ariki-Koike algebra is not isomorphic to just taking this finite dimensional algebra subject to the cyclotomic relation with HD. So this is because if you take, say, y2, it doesn't satisfy this cyclotomic relation. So in other words, tensor factors on different positions behave differently for this Ariki-Koike algebra. So you see a symmetry here. You only take a relation with respect to something on the first factors. The others are determined by that. It doesn't satisfy some universal local relation for each tensor factor. Okay. Maybe it's a good time to take a break. Okay, we'll resume in 10 minutes. So let's resume. So before proceeding to the proof of the basic theorem, let me give you maybe 3 more examples of the quantum Wreath product algebras. So this is very closely to the affine Hecke algebra, this degenerate cousin. So this degenerate affine Hecke algebra was first introduced by, I think, either Lusick and Dringfield for the study of Yangian or the graded version of the Hecke algebra. And it then proves to be related but not exactly the same as the affine Hecke algebra. So this analog is like the Lie group versus Lie algebra. Lie group is more complicated, but Lie algebra is the essential part. So here, the degenerate affine Hecke algebra is the essential part of the affine Hecke algebra. And you can define something like this. It has 2 types of generators. The polynomial generators Sxi and the symmetric group generators Sj. So, as always, we have the nice set of braid relations. And then in this case, since this is degenerate, you have a degenerate quadratic relation Si squared to 1. And as I also tell you, these Xi are polynomial generators, so they satisfy this commutation relation. And the cross relation between S and X used to be described in clauses. It's either, say, Xi plus 1 Si minus 1 if J is I plus 1, and when J is I minus 1, you get the other way around. And it commutes when neither. So I'm saying this algebra can also be realized as a quantum Wreath product algebra. You just take B to be the ring of polynomials. And then you have almost the same argument. You want to describe the S and R to be 0 and 1 so that you have a degenerate quadratic relation. And next, you want to describe how Hi interact with a tensor B. So this is again, the flip map. Now I think you only need to subtract 1. So, sorry, I meant x1 and 1x. And you have a similar lemma as in the affine Hicke algebra case. The row map is uniquely determined by this. Yeah, so -1 is -1 tensor 1 in this case, and so it then sends an arbitrary element to the de Major operator acting on this, and then multiply by -1 tensor 1. So this gives you the isomorphism by mapping Hi to Si, and then this xj is from putting x on the jth tensor vector. It's also the flip. Yes, it's also the flip. So at the moment, I don't have like any examples. I mean, they are very close. So a sigma can be the flip multiplied by some q power, but this is essentially the same. Yeah. So under a suitable normalization, this is always the flip map. Yeah. So I keep it there just because proving that is equally easy. So, but I want to be as flexible as possible.
There are examples where it's not just a flip map?
Oh, this flip map multiplied by a q power. No, not the example. Right, but all the proofs, arguments, do not really require. Yeah. So, okay. So here is some something probably less known. This is the affine zigzag algebra. So they are used by Kleshev and Robert Moves recently to study the imaginary strata of the KOI algebra. And so let me start with some background. So you actually need some thinking diagram of type ADE. It has to be simply laced. And then you can define its double quiver. Which means you replace a single edge by a double edge. And then you can define an algebra. So say K is in a commutative ring, then ZK gamma is firstly the path algebra of your double quiver modulo the following relations. So I should say first what's the path algebra first. So this algebra has as a vector space has a basis coming from all the paths on your thinking diagram. For example, if you have a thinking diagram of type D4, so any walk, say 1 to 2, 2 to 3, 3 to 2, this, without any relation, is an element in your path algebra. So this is, at the moment, infinite dimensional is out of control. You need to impose some relations, saying certain types of paths equals to 0 to make it a finite dimensional nice algebra. So the relations here we need is any path of length greater or equal to 3 has to be 0. So you only have those path of length 0, 1, or 2, which represents node, line, and some like path of length 2. But we don't want all the paths of length 2. They are 0 unless they are cycle. And for all the cycles, we don't want them to be the same. For example, this, you can have cycles starting from 2 to go from here, to go from here, or to go from here. We want to identify all 3 possible cycles. So the third relation is cycles at the same node has to be the same. So, which means as a vector space, this has a basis labeled by EI, AIJ, and CI. So the EIs corresponds to the node at the ith node. And AIJ represents the edge from I to j. And CI is the cycle at node I. And so the claim is we have a realization of this as a quantum Wreath product algebra. You want to choose B to be the zigzag algebra over the ring of polynomial. And then you choose S to be 0, R to be 1 tensor 1. So this is a degenerate case. And then sigma is the flip map. Rho is something technical, which I don't want to write down, but I want to give you a different flavor. So these so our construction does contain some exotic algebra that might be useful. And then, so this is one family of the other generalization. And to name also a few other examples, let me write here. Quantum Wreath product produces, say, Jinghui Weichang's Wreath Heck algebra. That's the degenerate Heck algebra for the Wreath product. And also Russell Savage. Frobenius Heck or neo-Heck algebra. So they have the purpose of studying this for the Heisenberg categorification, which I don't really understand, but it's good to have more connections. And also Ben Elias Heck categories. I think he used Heck type categories. So that's still a work in progress, but
I understand that sentence. So B is, so if B defined to be this zigzag algebra, S you choose, R you choose, sigma is chosen, rho is chosen, and what do you get?
Oh, sorry. I missed the punchline. So by this B, yes, is isomorphic to the affine zigzag algebra. In the title.
So we're choosing this affine diagram.
No. So you use the finite diagram, but you do an affinization. Yeah. So they define it like directly. They say, oh, you have to find an algebra subject to not only this relation, but a list of relations that people don't want to look at.
So you cannot define it from the affine diagram. You cannot define this.
I don't know how you identify, but I suspect. At least I don't see this from their paper. Yeah, I don't know. So I mean, this algebra is only used to describe some strata from the KY algebra, which is produced from an affine diagram. So I think they are connections, but I don't exactly know. Yeah. Right. Okay. So I was here. So I'm saying this is still a work in progress. Ben-Elias is trying to categorize the Nichols algebras, which are generalization of the positive part of the quantum groups. And he needs some algebra that are related to what we have to describe the Helm space for his categorification. But since he has not put it on archive, we'll have to wait. Okay, so let me tell you the idea of proving the basis theorem. So we had conditions from 1 to 5. We are showing that these all hold implies that there's the nice basis of this form. Okay, so in order to do this, I think it is helpful to recall Humphrey's proof on that TW forms the basis of the Hicke algebra of finite type. So what he did first is to consider something that already has the desired basis. So this is a free K module. And then he wants to show that there is a H module isomorphism between this and the algebra. And the way he does that is to use the algebra structure or ring structure on the endomorphism on the endomorphism ring. And in particular, he needs some right multiplication, Fs, that reflects the fact that you have a multiplication rule sending this to TWTS. So when I write this, this is actually illegal because the multiplication of this is not in epsilon. So you have to write it in clauses. This is either TWS or TW times some coefficient plus some other coefficient. And then there are some calculations to follow, and then he can show that this is isomorphic to that, and hence you have a basis. So you want to mimic what's happening here, but you'll get some technical difficulties. So we want to consider a free K module that has our desired basis. So you have the tensor algebra part, and then you need some part corresponding to the H. And then you essentially need to show that there is an A module structure on this guy. A is the quantum Wreath product algebra. So the B tensor D part is easy. You just take a left multiplication. But now you want to also act from the right of everything, this is the part is getting a problem. So we need right multiplication for any element in B tensor D, and we also need corresponding part for HIs. So this Fi, what we have in mind is some map sends an arbitrary element in the free module to BHW times HI, but this is illegal because this is not there. We have to resolve it. And also FA is sending this to that, which is also illegal at the moment. We have to resolve it. But there is a problem here. So since we have, how should I say? So you actually need to fix a reduced expression. So if you start with any arbitrary element here, you don't know what the ending element in your W is. So you don't know which, so I mean there are more than one way to resolve this, and you have to prove that no matter which reduced expression you have, you always get the same element. So in order to proceed the proof, you need to start with a choice of reduced expression for any W in the symmetric group. So let me call this universal reduced expression. This is defined for each W such that they are compatible from the right. So this can be proved. I mean, there exists such a universal choice of reduced expression. You can start with say the identity, and also and then the simple reflections, and then each time you define a reduced expression, you just choose one from the previous, and then you can proceed and find just one such choice of universal reduced expression. And then the problem is we want to show that this map is independent of the choice of this R. So the way to do it is to consider a filtration on epsilon. And the L part is just those elements with length less or equals to this chosen L. And then we have a analog of a Kashiwara square loop argument. We need to prove by induction these the following statements holds. So this is the target statement. R of L means Fa is independent of choice of R on the L filtration. So you start with L equals to 0, and then you want to prove by induction this holds. And then in order to prove it, you need some other statement. So QL means the quadratic relation. Basically, you have that Fi squared equals to Fsi. This is the choice of parameter Si, not the simple transposition. And then plus this and that. You want to show that this holds as endomorphisms on epsilon L. So by up, this is just because we are looking at the right action. So I put an up here. And then in order to prove this, you also need to consider similar statement for the multiplication, for the braid relation, and the Wreath relation. They are these. So each statement with this bracket number indicates that on which filtration layer it holds. So the proof goes like this. For each, so you have a grand loop like this. So you have a R from the previous fixed number L. It implies the W statement, and then the multiplication statement, and then the quadratic statement, and finally the braid relation statement. And from all these, you can prove the next reduced expression statement. So, and then, as I said, each step uses all the previous assumption on these statements plus those star relations. So this is like a really lengthy induction. You need to check all these things, and then this also convince you that all the relations we wrote down are sufficient. Yes. So this is the basis theorem part. The star relations are exactly the necessary and sufficient conditions you need in order to have a basis of the right size. Yeah. Okay, so the final topic of today is for the sure-while duality. So let me write down those lemmas I need in order to prove my theorem B. So the first one is we want to upgrade the Frobenius symmetric algebra structure from the base algebra to the upper algebra. And the conditions we need is that the trace map preserve the sigma map. Sorry, the other way around. The sigma map, the sigma map preserve the trace map. And also we need that R is invertible. Rho is 0. Then the quantum Wreath product algebra is also symmetric. So this is proved by a direct verification. So you just want to check that the new trace map on A is given by sending an arbitrary element to either 0 or the product of trace on each tensor factor. And then I want to now revisit the concept of the sure-while duality. So people have been talking about sure-while duality from many aspects, and the common statement is usually, oh, it has a double centralizer property. But there is something that's more essential and happening before having a double centralizer property. And so I think the source should be that you have a splitting of your action from the Hicke algebra side. So let me be precise. So for a Schur-Weyl duality, the usual picture is like this. So by double centralizer property, I mean you start with two algebras and check that each algebra is a centralizing partner for each other. But I'm saying you should really start with this guy first, and then define S to be the centralizing partner, act on T from the left. And then the source statement is that suppose that you have a splitting T as a direct sum Q for some right A module. Yes. So this is an isomorphism as A module. And the consequence is you can first define an inverse Schur functor. Which is hum. Putting the T on the right spot. This takes A to T as left S module. And then you can then check T is a projective S module because it's a direct sum of some free module inside. This is some homological formality. And then the second statement is there is an idempotent in S such that T is isomorphic to SE, and the centralizing partner is isomorphic to ESE. So this is the second level of a Schur-Weyl duality, that you have a idempotent, which is usually hard to construct. And then the third level is you can now get a Schur functor that goes from S module to ESE module for free, but you want to identify this with A. So this is the third level, and the question is, when does that happen? Yeah, yes.
How does the classical Schur duality fit into this?
Yes, I can tell you about that maybe in 4 slides. Right. I'll talk about examples too. But I mean, this is like the way I want to think of Schur duality now. So, to identify ESE with A, one can use a classical result. This is, I don't know the source, but I found this in Curtis Reiner. So I actually look at on one paper of König, Xi, and Slungard in 2000-ish, and they also said, oh, this can be found and is folklore in the huge volume of Curtis Reiner. It must be like known pretty early. but anyway, so the condition you need is A is a self-injective algebra, and T is a faithful A module. Then you can identify this. Right. So, okay, so let me write down the last ingredient, and I can tell you how these all patch up. So we constructed a way. This is vaguely speaking, you want to find a D distinct direct summand, which each isomorphic to B in your tensor space of B. If that holds, plus something else, this is rather technical and not a serious condition, then there is a canonical action on TA constructing by default tensor of TB such that you have the splitting. So to patch up everything, this is the idea. You have, so as I said, the three levels of Schur duality is there's a splitting, there's an idempotent, and also there's the Schur functor.
Just about the first level. So what is TB?
TB.
What is B direct tensor D or
D. D.
TB, what was TB?
So that's your choice. So for any quantum Wreath product, you have a base algebra B. You have to consider first a Schur-Weyl duality for your base algebra B, right? Okay, so for this, this is guaranteed by the splitting for A is guaranteed by our lemma if this happens. And for the most naive example is the type A Schur-Weyl duality, where you set TB to be the n-dimensional subspace vector space, and then you want n bigger or equals to D. Oops. So in like all these Schur-Weyl duality, you always find a condition on the rank. This tells you that if this happens, you can always find D distinct direct summand which isomorphic to B in your tensor space. And then this is the first step. And then once you have a splitting, you know that, oh sorry, I should write this down first. So from idempotent to Schur functor, we apply the lemma from Curtis Reiner. You need to check first. It is faithful, and also you have self-injectiveness. The faithful part comes directly from the splitting, so that is okay. And for the self-injective part, this follows from that A is a symmetric Frobenius algebra. And then this is another lemma. We show that when B is a symmetric Frobenius algebra plus something else, A is a Frobenius symmetric algebra, and then all this hold. And this may seem like a complicated machine, but it actually covers some very nice examples that we have in literature already. And also the new result when do you have a Schur-Weyl duality for the Hui algebra. So
If you take anything symmetric, then basically A will be symmetric.
theoretically, yes. Yeah, there are some conditions to check, but I don't think there are that many examples known. This is because symmetric Frobenius algebra is only defined for finite dimensional algebra. So for those affine cases, this does not hold. But I mean, there's still room to wiggle because for this, this is like the easiest way from idempotent to sure functor. But I totally believe that you don't really need to use this lemma to go from idempotent to sure functor. So for those affine Hecke algebra, I think it's likely that you can go from here to here without using Curtis-Reiner, and there must be a proof. I just didn't spend enough time on that. Okay, so the most naive example. Oh, maybe I didn't tell you, the Hecke algebra of type A, you can really consider this as the ground field quantum Wreath product HD. So B is just K. And then, as I said, those you have a naive action from B to the tensor space. So what is B module? What is splitting? You just want to find a d-dimensional subspace in your TB. Then you can upgrade this to a sure-vowel duality for the Hecke algebra. So pictorially, your TB consists of those basis vector Vn, Vd, V1. And the right action of B is just right multiplication. So KVD isomorphic to B, KV1 isomorphic to B. So as long as n is greater or equal to D, you have a direct sum B to the D sit inside your TB. And then when you upgrade this sure-vowel duality, you take the default tensor of TB. So pictorially, you have like D straight lines. This is the first Vn and the last Vn. So in order to construct a canonical action, you want to take the the tensor factor in an increasing order. You choose different direct summand for each of these strands. So for example, you can choose the first one here. I think I need a different color. So I have a V1 tensor, V2 tensor, all the way up to Vd. This is an element in the default tensor, and I want to generate an A module using this. And I can show that this provides the splitting that I need inside TA. So as long as n is greater or equal to D, I have construct a canonic action that corresponds to this splitting, and hence this recovers the usual sure-vowel duality. Okay, so the next example is when I take the Hu algebra, which is a quantum Wreath product of H sigma m twice. So in this example, B is the Hecke algebra of type A. So how do I construct these splitting on the B level, I take this picture and do it again, make it a higher level. So the condition here is actually that you need a TB to be n tensor m. So they are m many strands. And I know that there's a way to construct one direct summand here. But this is only half of that, because in order to apply my theory, I need 2 copies of these. So they are m basis element in this strand. I need a height m to construct one direct summand, which means in order to make my sure duality holds, the condition I will need for Hu algebra is m is greater than 2m. So if this holds, I can construct a tensor space for my Hu algebra to act on. And then I need, vaguely speaking, something like this. I'm being sketchy here, but I hope this makes sense to you. So I want to generate something by taking this tensor product with that tensor product. And this is isomorphic to the Hu algebra as a Hu algebra module. And then you have some other part that also does the job. You have a splitting, and hence you get a sure vowel duality. For the Hu algebra. And in particular, at the Q equals to 1 level, this is a sure vowel duality for such group algebra of something that's not even a complex reflection group. I think this is new. And they are... What is what? S. Oh, so yeah, that's the centralizing algebra for this canonical A action.
So do you know what it is? This description of this algebra?
So there is a basis. I mean, so you can think of it this way. So the Hu algebra is some subalgebra of the type A Hecke algebra, and also it contains the parabolic. So this canonical action here happens to be the type A tensor. So you can describe the Schur algebra as the subalgebra of SQNM tensor itself, with which contains SQN2M. So there's a I don't know if this is explicit enough for you, but there is some description right in between. Yeah, so this is like you take anything here that commutes with this action. Yeah, you can count the dimension, something like that. And then theoretically, what the next question you ask is how can you construct the corresponding quantum group using the BOM procedure? Right, so I think we haven't even tried to do it, but this is, I think, a reasonable question. Yeah. So, okay. All right, so I think I am about to run out of time. So let me say quickly. So for the sure vowel duality of affine Hecke algebras, I think the part is we cannot prove it this way, but we can still use the same viewpoint that the existence of splitting is more important. So all these ring conditions are just a sign that you can construct a splitting there, and the splitting actually contains the information you need. As long as we can prove from here to here without using the Curtis-Reiner lemma, we should be able to really find a universal proof for all the sure-vowel duality in the past. And this machinery can be applied to the sure duality for, what's the word? So there is some, I think it's called super yeah, I can't remember. This is one of the paper by S.F. and Kleshev. They prove a sure vowel duality in order to prove the Turner's conjecture. And I think their theorem is also a special case of this machinery. I'm just saying this contains more than just the classical results. And finally, I'll make some further connections. That's worth thinking. So, okay, so now we have a sure functor from SA mod to AM mod. And what we are doing at the moment is to upgrade this to a sure algebra functor from SQD to HQD module. This is because we have a Morita equivalence from HQD to AM plus the type A part. So one should be able to upgrade this to get a isomorphism for those sure algebra of type D, and also sure algebra for the Hu algebra and some type A sure algebra. So this, I think we have the sure functor part, but what we have in mind is to prove that this is a one cover. So there are some careful verification that one needs to do. I think we have an idea, but the proof has not been finished. But this, I hope, will come up in the coming months. And then some wild thought. So there is a non-isomorphism for the spherical affine Hecke algebra. You take the center of your affine Hecke algebra, and then you hit both sides by some idempotent to be constructed. This is called the Satake isomorphism. But this is very tempting. You look at this statement, you see if you replace this affine Hecke algebra with any quantum Wreath product algebra, especially the Hu algebra, what do you get? Can you actually construct such an idempotent, make this happen? And furthermore, based on this center of the affine Hecke algebra, the general form is the default tensor, invariant part of your default tensor. It has a orbit sum basis, which can be used to produce Macdonald polynomial. And then there's the Macdonald constant term conjecture. But I mean, if we take B to be the Hecke algebra, and then we have already the orbit sum and the Macdonald polynomial for coming from the Hu algebra, there is already a parallel setting. So there seems to be an analog of a Macdonald identity for the Hu algebra and potentially any quantum Wreath product algebra. And what is that? How do you prove it? And yeah, I think I don't have time to say something more. But I am saying, I think in general, the quantum Wreath product provides you a vessel to create statements. Once you know any statement for any of these 9 examples, it could make sense to ask the same question for the other algebra. Especially we have this new new addition to the Hecke algebra family. I think there are more questions one can think about. Maybe some of them are not important, but I think this could be interesting to some of you. Yeah, let me stop here.